Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. A three-phase star-connected 400-volt 50 Hz 4-pole induction motor has the following per-phase constants referred to stator side. R1 equals to 0.15 ohm, X1 equals to 0.45 ohm, R2 dash equals to 0.12 ohm, X2S dash equals to 0.45 ohm, and Xm equals to 28.5 ohm. The fixed losses, that is core friction and windage losses, amount to 400 watts. Using exact equivalent circuit, we have to determine the motor speed, stator current, rotor current, developed torque, output torque, and overall efficiency when the motor is operated at rated voltage and frequency at a slip of 4%. Let us first write down the given data. For rotor winding, resistance per phase referred to the stator R2 dash equals to 0.12 ohm and standstill leakage reactance per phase X2S dash equals to 0.45 ohm. For any value of slip S, expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.12 by 0.04 plus J times 0.45 ohm. That gives us 3 plus J times 0.45 ohm. This may be written in polar form as 3.03356 ohm at an angle 8.53 degree. For shunt branch, given magnetizing reactance per phase Xm equals to 28.5 ohm. Let us now calculate Jxm plus Z2 dash. Using values we get 3 plus J times 28.95 ohm. This may be written in polar form as 29.105 ohm at an angle 84.0837 degree. Now we shall determine equivalent impedance per phase. ZEQ equals to Jxm parallel with Z2 dash, that is equal to Jxm into Z2 dash divided by Jxm plus Z2 dash. Using values we get 28.5 at an angle 90 degree into 3.03356 at an angle 8.53 degree divided by 29.105 at an angle 84.0837 degree. That gives us 2.9705 ohm at an angle 14.4463 degree. Given line-to-line terminal voltage VL equals to 400 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.94 volt. For stator winding, given resistance per phase R1 equals to 0.15 ohm, and leakage reactance per phase X1 equals to 0.45 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1, that is equal to 0.15 plus J times 0.45 ohm. We have obtained equivalent impedance per phase ZQ equals to 2.9705 ohm at an angle 14.4463 degree. This may be written in Cartesian form as 2.8766 plus J times 0.74106 ohm. Let us now determine total input impedance per phase. Zin equals to Z1 plus ZDQ. Using values we get 3.0266 plus J times 1.19106 ohm. This may be written in polar form as 3.2525 ohm at an angle 21.48 degree. We have determined total input impedance per phase Zin equals to 3.2525 ohm at an angle 21.48 degree. Now we shall calculate stator current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 230.94 at an angle 0 degree divided by 3.2525 at an angle 21.48 degree. That gives us 71 ampere at an angle minus 21.48 degree. Expression for rotor current per phase referred to stator side I2 dash equals to JXM divided by JXM plus Z2 dash into I1. Given magnetizing reactance per phase Xm equals to 28.5 ohm. We have computed JXM plus Z2 dash equals to 29.105 ohm at an angle 84.0837 degree. Using values we get I2 dash equals to 28.5 at an angle 90 degree divided by 29.105 at an angle 84.0837 degree into 71 at an angle minus 21.48 degree. That gives us 69.5241 ampere at an angle minus 15.5637 degree. For three-phase induction motor, air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.12 ohm and slip S equals to 0.04 per unit. Therefore, Pg equals to 3 into 69.5241 square into 0.12 by 0.04. That gives us 43,502.404 watt. Expression for mechanical power developed Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.04 into 43,502.404, which is approximately equal to 41,762 watts. In polar form, stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 71 ampere at an angle minus 21.48 degree. For star connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 21.48 degree, that is equal to 0.9305 lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values we get √3 into 400 into 71 into 0.9305, which is approximately equal to 45,771.5 watt. Total power output PO equals to PM minus PR. Given fixed losses PR equals to 400 watts. We have determined mechanical power developed PM equals to 41,762 watts. Therefore, PO equals to 41,762 minus 400, that is equal to 41,362 watts. Now we shall determine overall efficiency of this motor. Eta equals to PO divided by Pin. Using values we get 41,362 divided by 45,771.5. That gives us 0.9037 per unit or 90.37%. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that gives us 1500 revolutions per minute. Now we shall calculate motor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.04 per unit. Therefore, Nr equals to 1 minus 0.04 into 1500, that is equal to 1440 revolutions per minute. Now we shall calculate developed torque. Td equals to Pg divided by 2 pi into Ns by 60. We have obtained air gap power Pg equals to 43,502.404 watt. Therefore, Td equals to 43,502.404 divided by 2 pi into 1500 by 60, which is approximately equal to 277 Newton meter. Expression for output torque. TSH equals to PO divided by 2 pi into Nr by 60. We have computed total output power PO equals to 41,362 watts. Therefore, TSH equals to 41,362 divided by 2 pi into 1440 by 60, which is approximately equal to 274.3 Newton meter. Now we shall learn how to determine equivalent rotor current per phase I2' using Thevenin's theorem. For this purpose, we shall remove the load, that is the equivalent rotor impedance per phase Z2' from this circuit. Now, the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0.15 plus J times 0.45 ohm. This may be written in polar form as 0.4743 ohm at an angle 71.565 degree. Rotor impedance per phase referred to the stator Z2 dash equals to 3 plus J times 0.45 ohm, that is equal to 3.03356 ohm at an angle 8.53 degree, and shunt impedance per phase Z0 equals to JXM equals to J times 28.5 ohm. This may be written in polar form as 28.5 ohm at an angle 90 degree. Let us now calculate Z0 plus Z1 using values we get 0.15 plus J times 28.95 ohm. This may be written in polar form as 28.9504 ohm at an angle 89.7031 degree. Now we shall determine Thevenin's voltage. V Thevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 28.5 at an angle 90 degree into 230.94 at an angle 0 degree divided by 28.9504 at an angle 89.7031 degree, that is equal to 227.3471 volt at an angle 0.2969 degree. To determine Thevenin's impedance, let us short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 28.5 at an angle 90 degree into 0.4743 at an angle 71.565 degree divided by 28.9504 at an angle 89.7031 degree. That gives us 0.46692 ohm at an angle 71.8619 degree. This may be written in Cartesian form as 0.14536 plus J times 0.44372 ohm. Now we shall compute Z Thevenin plus Z2 dash. Using values we get 3.14536 plus J times 0.89372 ohm. This may be written in polar form as 3.26987 ohm at an angle 15.8619 degree. We have determined Thevenin's voltage V Thevenin equals to 227.3471 volt at an angle 0.2969 degree, and Thevenin's impedance Z Thevenin equals to 0.46692 ohm at an angle 71.8619 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash back to this circuit. We shall now compute the load current, that is the rotor current per phase referred to stator side. I2 dash equals to IL equals to V Thevenin divided by Z Thevenin plus ZL, or V Thevenin divided by Z Thevenin plus Z2 dash. We have computed Z Thevenin plus Z2 dash equals to 3.26987 ohm at an angle 15.8619 degree. Using values we get I2 dash equals to 227.3471 at an angle 0.2969 degree divided by 3.26987 at an angle 15.8619 degree. That gives us 69.52787 ampere at an angle minus 15.565 degree. Expression for induced EMF per phase E1 equals to Z2 dash into I2 dash. We have obtained rotor impedance per phase. Refer to the stator. Z2 dash equals to 3.03356 ohm at an angle 8.53 degree. Therefore, E1 equals to 3.03356 at an angle 8.53 degree into 69.52787 at an angle minus 15.565 degree. That gives us 210.917 volt at an angle minus 7.035 degree. We have obtained induced EMF per phase E1 equals to 210.917 volt at an angle minus 7.035 degree. This may be expressed in Cartesian form as 209.3291 minus J times 25.8322 volt. Let us now calculate stator current per phase. I1 equals to Et minus E1 divided by Z1. We have computed stator impedance per phase. Z1 equals to 0.4743 ohm at an angle 71.565 degree. Using values we get I1 equals to 230.94 minus of 209.3291 minus J times 25.8322 divided by 0.4743 at an angle 71.565 degree. That gives us 33.68 at an angle 50.0846 degree divided by 0.4743 at an angle 71.565 degree. That is equal to 71 ampere at an angle minus 21.4804 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.